Brought to you by the Astro Youth House chapter from STEM Arts Lab, Space on Earth is a student-led podcast that inspires listeners who are curious about space to explore the wonders of the universe through the voices of young thinkers, creators, and dreamers.
Each episode blends personal curiosity with scientific discovery, from the mysterious depths of black holes to the practical impacts of space on Earth, like GPS, climate science, and medicine.
Hosted by STEM Arts students from Taos, New Mexico, this podcast draws connections between space, art, and science, how these things all impact us here on Earth, and their meaning to humanity.
You'll hear raw, insightful conversations about topics like light pollution, the overview effect, lunar exploration, and the societal impact of the space race.
Whether you're into exoplanets, dark energy, or just stargazing from your backyard, Space on Earth makes space personal, accessible, and inspiring. We believe that space isn't just for astronauts and scientists, it's for everyone.
Join us on this adventure as we explore the cosmos from Earth, one story at a time.
Special thanks to the Lore Foundation for helping launch this podcast.
Hi everyone, welcome back to Space on Earth podcast. Today we're going to be talking about dark matter, the history, the science, the math, the future, and any other questions and thoughts that we have. Today I'm joined by Wyatt Wade and Pascal Heitzman. I will also be hosting today. My name is HattieRose. You guys have seen me frequently on these episodes, and we're really excited to get started today. Pascal is a new joining host. Pascal, do you want to talk a little bit about yourself and introduce yourself to our listeners?
Yeah, hello everyone. My name is Pascal. I'm a lover of art, music, and of course, math and science. And I'm really glad to be here today and talking with these other amazing people.
Great. Thank you so much, Pascal. So, dark matter originally started with Fritz Zwicky, who was studying the Coma galaxy cluster, which is a massive group of galaxies bound together by gravity. He used the Wyatt theorem, a physics equation that relates to kinetic energy and gravitational potential energy in a stable system. What he found was the galaxies in Coma were moving way too fast, and based on visible mass, stars and gas, the cluster should have flown apart, but it didn't. So the conclusion was there must be extra invisible mass holding it together. He called it Dunkel Materie, dark matter. And then in the 1970s and 1980s, Vera Rubin studied how stars orbit inside spiral galaxies.
That is really cool, Hattie. Pascal, what did Rubin actually study?
So Vera Rubin primarily studied the Andromeda galaxy, and she studied the rotation of stars. And the conclusion of her work was that galaxies, if they were based only on the mass that they had from stars or visible sources that humans could at the time detect, would fly apart. And so her conclusion was that there was a matter that we as humans could not measure that was helping keep these galaxies together, because otherwise mathematically they would fly apart due to the velocity of the stars. She tracked the stars in Andromeda's galaxy for, I believe, about 10 years, from the 1970s to the 1980s. And one of the reasons she chose this as her field of study was actually because she wanted to be able to live in DC and wanted to be able to study stars in a city with her family, which I think is really cool. And HattieRose, can you talk a little bit about the math and how that led to the discovery of dark matter?
Yeah, so scientists did something pretty simple. They measured how fast stars move inside galaxies, and they measured how fast galaxies move inside clusters. So using the known laws of gravity, they asked, how much mass must there be to keep something moving that fast without flying away? When they did that calculation, they got an answer. Then they compared it to how much mass they could actually see from stars and glowing gas. But the visible matter wasn't even close to enough. If only the stars we can see were there, gravity would be too weak, the fast-moving stars could escape, galaxies would slowly tear themselves apart, and clusters of galaxies would slowly drift away from each other, but they don't. These galaxies are stable and clusters stay bound. So the only logical conclusion was there must be extra mass creating gravity, mass that doesn't give off light. That invisible gravitational mass is what we call dark matter. So when astronomers look at stars orbiting inside galaxies and galaxies orbiting inside clusters, they measure velocity using Doppler shift. If something moves towards us, light shifts blue, and if it moves away, light shifts red. From that shift, we calculate speed. In the Coma cluster, Zwicky measured galaxy speeds around 1,000 kilometers per second. So to stay gravitationally bound, motion and gravity must balance. So Zwicky plugged in the observed velocity and the size of the cluster. The cluster needed 7 times more mass than what was visible in stars. Pascal, I know that you know a lot more about this, so do you want to talk a little bit more on it before we move on to the next topic?
Yeah, I'd love to. So, some cool little tidbits are the person who originally coined the phrase dark matter, Fritz Zwicky, when he estimated how much dark matter there was compared to normal matter, the ratio is like 600 to 1. But nowadays, the general scientific consensus is that the ratio of dark matter to normal or visible matter is 6 to 1, not 600. So it's kind of interesting to see how science has evolved and how even the first person who kind of thought about this, his ideas were able to be refined by later scientists into more accurate information. And that's just a cool way of as humans and scientists continue, whenever we discover or learn new things, we're always refining our knowledge.
And something cool that has recently been in progress is that the Nancy Grace Roman Space Telescope is allowing us to once again refine our knowledge of dark matter, and Wyatt is going to tell you a bit more about that.
Yeah, the Nancy Grace Roman Space Telescope, or just Roman Space Telescope for short, is NASA's next major space observatory designed to study dark energy, dark matter, exoplanets, and the large-scale structure of the universe. Often described as a wide-field successor to Hubble, Roman combines the sharp imaging power of a space telescope with an enormous field of view, allowing it to survey vast regions of the sky quickly and precisely. But how does this help us learn more about dark matter? Roman will not detect dark matter directly. Instead, it will measure how dark matter bends light from distant galaxies. So, the main method that Roman will attempt to do this is called weak gravitational lensing. Basically, dark matter has gravity, even though it does not emit or reflect light. When light from distant galaxies travels toward Earth, it passes through regions filled with dark matter. The gravity from that unseen mass slightly distorts the galaxy shape. That effect is called weak gravitational lensing. Roman is especially good at this because Roman has a wide field of view 100 times larger than the Hubble Space Telescopes, actually, which is crazy. It's a crazy improvement. It also has extremely stable optics, and it has infrared sensitivity, which means it can see very distant galaxies. By mapping how dark matter is distributed, Roman will help scientists understand how dark matter clumps and form structures, and also test models of how galaxies form and evolve. Oh, it'll also study how dark matter interacts or doesn't interact with normal matter, which is really cool. Also, Roman will also observe strong lensing, where a foreground galaxy bends light so much that creates arcs or multiple images of background galaxies. These systems allow precise measurement of dark matter in individual galaxies and clusters. Roman will actually launch in September of this year on SpaceX's Falcon Heavy from Florida. So that'll be really cool. They've been working on or building it for the last 4 years, I think, maybe more. But it's going to be really exciting, and I can't wait to see what it discovers and teaches us. Pascal, do you want to talk about redshift?
Yeah, I'd love to. Redshift, which is how scientists measure how far away galaxies are, they're able to do this because atoms and therefore stars emit certain wavelengths based on the elements that are in the stars. These emissions can be placed on the electromagnetic spectrum, specifically the visual light portion. So Roy G. Biv, red, orange, yellow, green, blue, purple, violet. And when an object is retreating or moving quickly away from the observer or Earth, it can cause a shift towards the red part of the spectrum. How far away galaxies are based on the expansion of the universe. So as the universe expands, galaxies will move farther away from us, and we can tell how far a galaxy is away from us because the universe has expanded, and so galaxies that are farther away from us have shifted towards the red part of the visual spectrum. So when we talk about redshift, or this is also referred to as the Doppler effect, we're talking about how light shifts towards the red part of the spectrum when essentially it's farther away from us as Earth, or from Earth.
So before we move on to the next topic, just a quick summary of what we talked about today. We talked about the beginning of dark matter with Fritz Zwicky and Vera Rubin, and the calculations and the coma clusters, the science and the math parts, the Nancy Grace Roman Space Telescope, and the redshift. Next, we're going to be talking about a couple of thoughts that we've had over the past few weeks. This one's from Pascal, and she mentioned humans have very limited perspective abilities, and we use technologies to expand our ability to understand the world. What do you guys think about this?
Yeah, so I love history, and so I always think it's interesting to see how outside circumstances have pushed science, especially into becoming better and expanding how we can see the world. So, for example, in World War II, because of the use of submarines and U-boats, I believe the Allies had to develop radar technology and go deeper into radar and understand radar on a deeper level in order to counter this weapon used by the Axis. But that then also allowed us to expand after the war our perspectives in other scientific areas like space. And it's just kind of cool how we have these shifts towards progress, and all the time we are developing better ways to understand the world around us, because us as humans can only see a small portion of the visible electromagnetic spectrum. And so we're always pushing our limits and using technologies that we build to expand our perspectives to be able to understand our universe better. And yeah, so I just think that's a really cool concept. And it's like we have atmospheric distortion and we just have a clear picture of stuff when we put it in space because there's less barriers. So that's one of the reasons why we have expanded into space. Wyatt, can you talk a little bit more about why we have telescopes in space instead of just on the Earth?
Pascal, that is a very good question. I can answer that in one word: science. Science is very valuable because it provides a reliable way to understand reality, solve problems, and most importantly, improve human life. Where would we be if we didn't discover electricity or missions like the Nancy Grace Roman Space Telescope? All the other things we've done, like the Hubble Space Telescope and the James Webb Space Telescope, which we launched a couple years ago, are examples of science expanding human knowledge beyond Earth. Science is beneficial because it produces knowledge that is testable, reliable, and useful. It improves daily life, drives innovation, and helps humanity understand its place in the universe.
Thank you guys. That was like really good answers. I was also curious, how much of the universe can us as humans biologically understand? I'm pretty curious about this as well, so I'm gonna answer first and I'll pass it on to you guys. So I think it's pretty difficult for our brains to even consider things that could be happening in space or in the universe at all. So I don't know the biological terms, but I think it's pretty difficult for us to even consider like that there could be, we don't know what happened to start the universe. Many people have different theories, but nothing is proven. And I think it's just kind of hard for our brains to even conceptualize the idea of that. I've seen some theories about how there's been multiple Big Bangs, like over and over and over again, which I think is really interesting. But I'm not sure we will ever figure that out in our lifetimes. We might. That'd be very cool. But yeah, I think that there's so much of the universe as well that we also just can't biologically understand the amount of space. We don't really have the resources right now, but I think it's just really difficult to understand anything that's going on anyways. That's kind of my thoughts on it. Do you guys want to share anything on it?
Yeah, I totally agree with everything you just said. It's also so interesting because us as humans, evolutionarily, we weren't really designed to look up into the stars and try and figure out the distance between stars. And a lot of our evolution is based around hunting, gathering, survival. And so concepts like really, really, really small numbers and really, really, really big numbers, or even the fact that something is light years away and what light years actually relate to in human years, and in a sense, how small of a span of time we've kind of taken up, and like how the difference in scale between what we as humans on a day-to-day like level like experience versus what space experiences, because space-time is so much bigger than our human experience. And it's just so cool to think about how like we might not always be able to like fully conceptualize it, but it's still there. And like just the idea that a space day is so, so, so much longer than a human's day. And I just think that's a really, really cool idea. Yeah. And the next bullet is a little bit of a reach, but you guys know I think it's a book and a movie. I've only watched the movie though. I think it's called Arrival. It's about the aliens that land on Earth and have a different perception of time. I think it might be a bit of a stretch, but humans perceive time linearly. That's not necessarily how it could be. But I also think that's a bit of a stretch. And Wyatt, do you have any cool thoughts about this?
Yeah, when Hattie said how much of the universe can us as humans biologically understand, I kind of just immediately went to like how big space is. Think of a banana, right? I did the math a couple of weeks ago. I still have the piece of paper on my desk. It would take about 2.1 billion bananas lined up end to reach from Earth to the moon. That's a lot of bananas. Space is huge. It's hard to visualize that many bananas just from Earth to the moon. Then I did the math for the Earth to the Sun. That is 831 billion bananas. That is so many. Now, okay, let me actually do a little bit more math here. Prove my point even further about how big space is. From our sun to the next nearest star, Proxima Centauri, that's about 4.24 light years away from us. How many bananas would that take? 223 quadrillion bananas. That is over 100 million times farther than the distance from Earth to the sun. That is a lot of bananas. Yeah, guys, space is huge, and we should explore as much of it as we can and just learn as much information as possible.
Thank you, everybody, so much for listening today. I hope you guys enjoyed our discussion and all the information that we shared on dark matter. I hope this episode provided any insight to you guys, and I hope to see you next week. Thank you so much for listening. My name is HattieRose.
I'm Wyatt.
And I'm Pascal.